the biggest challenge thus far has been ultimately error correction. Can you just talk us through what you have just achieved?
Yeah, the biggest news for today is that we developed a new, very high quality quantum chip. And this enabled two breakthrough computations. And one is an error correction, where we showed for the first time that as we use more qubits, the error rate comes down, and it comes down exponentially. The second important achievement, breakthrough achievement, is that we did a benchmark computation, took just 5 minutes on our new chip, that would take the top supercomputer 10 septillion years to perform. So 10 septillion, audience may not know, that's a 1 with 25 zeros. So it's a mind-bogglingly long time.
And it took 5 minutes. What I want to understand is what this benchmark test is, benchmark random circuit sampling. What does this prove?
Yeah, so this benchmark problem, we often say, is not a problem that people on Main Street have yet. But it's a suitable benchmark to compare different quantum processors to each other, or to compare quantum processors, quantum chips, against classical computers.
What's so mind-boggling about quantum more generally is that we have been talking about it for decades, but it always feels another 5, another 10 years off. Is it different this time, Hartmut?
Yeah, quantum computing is definitely not that field. There is steady progress. And our new chip that we just released, Willow, will form the basis to start doing useful computations that will enable or solve problems that humankind has.
Let's talk about those problems then. Everyone immediately goes to healthcare, drug discovery. Is that the most obvious place with which this sort of computing is going to be helpful?
Yeah, so the well-understood killer application of quantum computers is to model systems where quantum effects are important. And that is more often the case than you may think. For example, if you want to understand how drugs, pharmaceuticals, bind to cells, or if you want to design a nuclear fusion reactor, or something as mundane as improving the batteries for an electric car, all these engineering challenges involve quantum problems. And their quantum processors are just a tool of choice to solve those problems.
Hartmut, put it in the perspective of generative AI, the hype that our audience that we have had over the past couple of years. What does quantum mean for that? Is it superior even in its effects versus generative AI? And does it suffer the same issues in terms of energy and infrastructure?
I wouldn't compare it in those terms. AI as well as quantum computing will be the most transformative technologies of our time. But there's a lot of cross-fertilization between AI and quantum computing. So AI can help work for quantum chips to work better, and vice versa. There are many key computational tasks in AI where a quantum chip will just be the tool of choice to handle those.